In this video, the entire process of calculations for creating a factor analysis by the principal component method will be demonstrated. The purpose of this is to make the conceptual and mathematical basis of the method as clear as possible. So in order to do that, we're going to use a small and artificial simplest case data set. And I will show this to you in a 15-step process, all using Excel. As you can see here at the bottom, I have steps 1 through 15 laid out. Now suppose that we have 6 subjects in a research study on cognitive development in adolescent males, and each of the 6 males have been measured on 3 variables: a test of verbal ability, a test of mathematical ability, and a test of logical reasoning. And here are the 6 males, and their scores on each are like this. Al has 8, 12, and 16. Bill has 6, 10, and 20. 5, 4, 9 for Charlie. Dan has 5, 10, 15. 4, 16, 20. And last, Frank has 2, 8, and 10. So this right here can be considered the data matrix for these 6 persons. So the first step is to create a covariance matrix from the raw data. So we need the mean vectors here. So what I'm going to do is make this equal to the average of this first column, and then drag that across. So we have 5, 10, and 15 for the average of verbal, math, and logic across the 6 males. Then next we need the matrix of deviations away from these means, which I have labeled X sub C. So this is going to equal our data matrix minus our means matrix. And don't forget to hit Control-Shift Return. Now the subscript on here, C, for the deviation score data stands for centered. And we learned how to do this, get this deviations matrix in video 3.2. The centered sum of squares and cross products, CSSCP matrix, can be found by pre-multiplying the deviation scores by the transpose of the raw score matrix. And we talked about this in video 3.8. So what we'll do is matrix multiplication, and I'm going to take the transpose of our data matrix here, and that's going to be multiplied by the deviation scores here. Control-Shift Return, and there's our CSSCP matrix. Now the last part of step 1 is getting the covariance matrix, which I have labeled S, and it's obtained by dividing the CSSCP matrix by the degrees of freedom, which in this case is 5 because we have 6 people, so you subtract 1, and it's 5. And we talked about this one in video 3.9. So what we do, we have this equal to this matrix divided by 5, and we get the covariance matrix, and that's step 1. And then in step 2, the covariance matrix is transformed into a correlation matrix by pre-multiplying and also post-multiplying it by a standardizing matrix E, which is, if you recall from video 3.12, is a diagonal matrix of reciprocals of standard deviations. So in this case, E would equal 1/2, and it's a diagonal matrix, so all the off diagonals will have zeros. So it'll be 1/2, and then here we have 0.3, and then 0.2. Which what I just demonstrated and did was rounding, actually. Since I said the standardizing matrix E is a diagonal matrix of reciprocals of standard deviations, we know from a covariance matrix that the diagonals are variances. So what we want to do is take the reciprocal of, well, we want to take the square root of that to get standard deviations, and then take the reciprocal. So 0.5 is actually 1/2. And then this 0.3 is actually 1/4, because the square root of 16 is 4, so 1/4, which will round to 0.3. And then we're going to have 1 over, we can make this equal to 1 over the square root of 22.4, which is 0.2. If we wanted, we can extend this out. So the next step would be to do matrix multiplication, and we're going to need this to do this 2 times. So we'll take E times S times E again. And there you go, we have our correlation matrix to finish up step 2 here. So now we can move on to step 3, where we are ready to factor the correlation matrix using the method of successive squaring, which we talked about in video 4.7. So I've copied and pasted our correlation matrix here. So if you call, what we want to do first is get a row sum vector, S sub 1, and it's created from our matrix R, the correlation matrix, by post-multiplying R by a vector of 1s right here. And that's our row sums. And then this S sub 1 vector is normalized to create a K sub 1 trial eigenvector whose largest value is 1. So this will be equal to S1 divided by the max value of S1, which is 2.204, to give us those values. Next, R is squared to obtain R squared, and R squared is post-multiplied by a vector of 1s to get the S sub 2 vector, which we'll then normalize to have 1 as its largest value to become a trial eigenvector K2. So here we're going to have R times R to get R squared. We're going to do lots of matrix multiplication here. We're going to get the row sums, and then the trial eigenvector K2 divided by 4.412, since that's the largest one. Sorry. I'll delete that. Sorry, I didn't mean to do matrix multiplication, did I? Divided by the largest one. Okay, so that gives us 1. Now we can compare the trial eigenvectors K1 and K2 to see whether they converge with an acceptable tolerance. We see that they do not, because the values are different here. So the correlation matrix is squared again. So we continue this process until we see 2 trial eigenvectors that converge. And I'm going to continue to do this, and as you can see, as I've laid out, I've kind of already given the answer, but I'll just quickly continue here. Looks like we're getting closer. And we'll do one more. The method of successive squaring isn't that bad when you use Excel, as you can see. I'm going pretty quickly. Okay, now, as you can see, these are pretty accurate. We can see that k sub 8 and k sub 16, those the last two trial eigenvectors, they agree to 3-place accuracy, pretty much. So the trial eigenvector k sub 16, we will normalize to 1, and that will become the true eigenvector k1. The magnitude of a vector is the square root of its sum of squares. That is the square root of the value to which is currently normalized. In this case, it's the sum of squares. It can be found using this. Use SUM for sum of SQ squares, parenthesis, and then we'll highlight this vector. And we find the sum of squares is 2.154. So the final trial eigenvector k sub 16 is therefore normalized to 1 by dividing each entry in the vector by the magnitude of that vector, which is the square root of 2.154, which you can see here is 1.467, and that to become the true eigenvector k1. So this will be equal to k sub 16 divided by 1.467. So we get 0.365, 0.635, 0.681 as the true eigenvector k1 to end step 3. So let's move on to steps 4 through 7. I put our correlation matrix in here again. I put k1, which we just calculated. By definition, the vector of factor loadings is the eigenvector normalized to its eigenvalue. The eigenvalue is found by using the fundamental eigenvalue-eigenvector equation, which I have right here. So let's do that. We're going to have a correlation matrix times the true eigenvector k1 that we got. And turns out if you take this true eigenvector again and multiply it by 1.971, it works out. And we have the same thing here. And we talked about what we just did in videos 3.37 as well as 4.7. Now for step 5, the eigenvalue for the first factor is therefore found to be 1.971, and the corresponding desired magnitude for the first factor is a square root of that, square root of lambda. As we can show here, square root of lambda, it's 1.4039. Next, the normalized eigenvector k1 is transformed into f sub 1, the vector of factor loadings on factor 1, by multiplying each value in the k1 vector by the desired magnitude, that is, by the square root of the eigenvalue. So we're just normalizing a vector to a particular value, and I wrote the formula here. So we're going to do matrix multiplication, and we're going to take k1 and multiply it by the magnitude, and we get those values. And that will end step 5. And once again, this is the factor loadings for factor 1, 0.512, 0.891, 0.956. So we have now successfully extracted factor 1 from the correlation matrix. To now extract factor 2, we must first remove all of the variance and covariance in the original R matrix, the correlation matrix, that has been accounted for by factor 1. This is done by creating a G sub 1 matrix, which we call the matrix of first factor products. And you do that by post-multiplying the vector of factor loadings F1 by its transpose in this formula. So we're going to do matrix multiplication again. Take F1 and multiply it by its transpose. To get those values. So by doing that, we get G1, the matrix of first factor products, completing step 6. Now let's go to step 7. It's important to explain in step 7 that the diagonal of this G1 matrix, so these values here, is the square of each of the loadings on factor 1. In other words, the communalities, the amount of variance that factor 1 accounts for in each of these 3 variables. The off-diagonals in G1 matrix give the amount of covariance in each pair of variables accounted for by each factor. We subtract this G1 matrix from the R matrix to find out how much variance and covariance is left over from after factor 1 is extracted. In other words, the amount of variance, covariance not accounted for by factor 1, which is what we want to get at. So we do that here. So we can say this is equal to R minus G. And the resultant matrix is a matrix of first factor residuals, symbolized by R sub 1. The diagonal entries in this residual that are right here indicate what proportion of variance in each variable is not accounted for by factor 1. So we can see 73.7% here is not accounted for, and as we go down it gets less and less. And the off-diagonal entries indicate how much covariance in each pair of variables is not accounted for by factor 1. So this matrix indicates how much more factoring needs to be done. That is how much in each of the variances and how much in each of the covariances remains to be accounted for. So we can see here going to the G1 matrix, once again the matrix of first factor products, which is the square of each of the loadings on the factor 1, giving the communalities or the amount of variance that factor 1 accounts for in each of the 3 variables. That was a mouthful, but just looking at it, variable 3 has 0.914 variance units out of 1, or 91.4% accounted for, leaving 0.086 or 8.6% to be explained. It is very well accounted for by the first factor. And as I just mentioned before, looking at variable 1, it still has 73.7% left to be explained. So we're ready to move on to step 8 now. And we are ready to extract factor 2 by the method of successive squaring that we did, if we go back here to step 3 that we did. So we're going to do this in step 8 again, but it's for factor 2. So we're going to get the trial eigenvectors for each successfully squared R matrix until convergence is reached. So as you can see, what I input here is R sub 1, the matrix of first factor residuals that we need. So we need to figure out from here what else can be accounted for in factor 2. So let's get on with this. Find the row sums. Divide it by the max, which is the top one here, 0.322. Which will give us 1, And then when we do Control-Shift-Return, it gives us that. And we can continue here. We're going to square R. And I'm actually just going to continue that here. Continue squaring. So we have R to the 4th. And now let's go all the way to R to the 8th. Now let's find the row sums for each one. And then the trial eigenvectors. All right. So looking at it here, we know, we can see here that they finally converge when we get to R to the 8th. So we can take the last trial eigenvector, K8, and find the sum of squares. Which will give us 1.212. So the magnitude of this is the square root of that, so it's 1.101. And what we're going to do is find the second true eigenvector of matrix R, the K2 vector, by calculating it by normalizing the last trial eigenvector to 1. So we're going to divide each entry in that vector by the magnitude. So take K8 and divide it by the magnitude, which is 1.101. And there you go. That's the end of step 8, so let's move on to steps 9 through 14. We're almost there. It's a similar process of what we did before. This looks familiar. We had in steps 4 through 7. And if you haven't noticed, I'm kind of going through the rainbow with the colors here because I'm a little bored. So I hope this excites you a little bit. Probably not. But we have our R matrix here, which we got from step 2. And then our second true eigenvector of matrix R, which we got from step 8. And we're going to multiply these. And turns out the eigenvalue, or the lambda that we get here, is 0.887. And let's double check with that. So we should get the same thing when we multiply these together, which we do. Of course, there's rounding error there. So we have obtained the corresponding eigenvalue from this equation that we've been using. To finish step 9 and step 10, the corresponding desired magnitude for the factor is found by taking the square root of that. So we get 0.9418. The normalized eigenvector K2 is converted into the vector of factor loadings, F2, by multiplying each value in the K2 vector by the desired magnitude, which I've shown in this formula. So let's do matrix multiplication, our favorite thing to do in the world. Take K2, and let's take our magnitude of that, the square root of that eigenvalue, to get our matrix or vector for the factor loadings for factor 2. So we have 855, negative 0.38, negative 0.104 to end step 10. Now you see here we're going to get G2, the matrix of second factor products, and that's obtained by post-multiplying F2 by its transpose, like we showed in steps 4 through 7. Actually, that was, I believe that was step 6. So this is equal to F2 times the transpose of F2. And then this matrix of second factor products is subtracted from the matrix of first factor residuals to obtain the matrix of second factor residuals. So we need R1 again, the first factor residual matrix. So I'm just going to type that in real quick. It's 0.738. Then we had, it was negative 0.306, negative 0.110. And if you're wondering why I'm typing this all in, we got this in step 7 here, but because I use matrix multiplication, I can't copy and paste it. So that's where I'm getting this from. I can copy and paste these values because it's a symmetric matrix. This was 0.028. And on the diagonals we had 0.738, 0.206, and on the third variable 0.8085, excuse me. So now let's do this. We have, this is equal to R1 minus G2, or in other words, the matrix of second factor products subtracted from the matrix of first factor residuals. And there we go. We get R sub 2, the matrix of second factor residuals. Now in this example, we are only going to extract 2 factors. And since we're only extracting 2 factors, this is the final matrix of residuals. This matrix contains the amount of variance and covariance not accounted for after the factor analysis is completed. It is an important matrix for interpreting the results of the factor analysis. And as we talked about before, if you look at the diagonals here, that will show you what is not accounted for, the variance not accounted for. So that's just 0.7, 6.1%, 7.4%, which is not a lot, so we could probably stop there with 2 factors. So that was the end of step 12. In step 13, we would just repeat steps 8 through 12 if we wanted to have more factors. Now here's what step 14 is. In step 14, we examined the diagonal of the final matrix of residuals to determine how much variance was not accounted for in each variable, which I just talked about a little bit. We also examined the off-diagonal elements to determine how well the correlations for each pair of variables are reproduced by the factor solution. So once again, the diagonal elements give us variance information and the off-diagonals give us covariance information. So going back and looking at the variance information, we can see the 2-factor solution does very well in accounting for the variance in variable 1, because we have less than 1% variance not accounted for. It doesn't do as well in accounting for the variance in variables 2 and 3, where the proportion of variance not accounted for is 6.1% and 7.4%, but I think that still does pretty well. Now looking at the covariance information, it tells us 2 things. It tells us how far off from the factor analysis is in accounting for the correlations, and whether the factor solution over or underestimates those correlations. The entry for the correlation between variable 1 and 2, we can see here, is 0.019, indicating that we have underestimated the actual correlation, but by a small amount. The entry for the correlation between variable 1 and 3 is about the same, but with a negative sign. Negative 0.021, indicating that we have overestimated the correlation this time, but not by very much. And it is a little confusing because you'd think a negative would be underestimating and positive would be overestimating, but it's the reverse, because remember, this is a matrix of factor residuals, talking about amount of variance and covariance not accounted for. The entry for the correlation between variables 2 and 3 is negative 0.067. So have we overestimated or underestimated? Like I just stated, we have overestimated that amount by almost 7%, 6.7, 6.8. All right, let's move on to the last step. Are you ready? Step 15. This is the final step in which we adjoin F1 and F2, which are the factor loadings, the vectors of factor loadings, to create the matrix of factor loadings F, which is just here, and complete the factor analysis summary table. So I've already created the table. I just left some things blank, but here we can find factor loadings, which once again was F1 and F2 that we calculated in step, in this one I think it was step 4 or 5 that we did, and then step 10 we got here. So I just copied and pasted them there. Once the factor loadings are entered in the table, the other entries can be calculated from them. So the communalities for the two factors are the squared factor loadings. So we just take the factor loading and square it here. And I can move that down. Oops. And then let's move that over as well. So that's pretty simple. The total communalities are the sums of the individual factor communalities by rows. So we just take the first one plus the second one and 0.993. We can drag that down to make that easy to get the total there. Okay. The eigenvalues are the sums of the communalities by columns. So we'll take this is equal to the sum of those three above it. Drag that over. Pretty simple. Then the percents of eigenvalues are the eigenvalues divided by the number of variables in the analysis, and then multiplied to 100 to convert them to percents. Let's drag that over as well. So this is going to equal the eigenvalue divided by, we have 3 variables in the analysis, so divided by 3, 65.7%. Let's drag that over. And we can see 95.3% is the total. The uniqueness values for each of the variables are calculated by subtracting each of the total communalities from 1. So we can have this equal 1 minus the total communality and 0.007. Now that should look familiar. It is actually the diagonals that we got on our matrix here. And let's continue to drag this over to complete our table. Isn't it beautiful? So the uniqueness column of this summary table is a new one introduced in this section that we didn't talk about before. What it does, it's an indication of the proportion of variance in each of the variables not accounted for by the factor solution, which, if you recall, that's what this R sub 2 matrix is on the diagonals is the variance not accounted for. So for example, the total communality for the reasoning test or logic is 0.927, indicating that 92% 2.7% of the variance in that variable is accounted for by the two-factor solution. The amount of variance not accounted for is 1 minus that, which is 7.3%. So that's the uniqueness for that one. When using data to do a factor analysis, which we'll do on a supplementary video to this, uniqueness is one of the default statistics reported. Now, before we finish here, I did want to mention something else that is very important. The factor loadings can be used to interpret the identity of the factors in terms of the common elements that load highly on each factor. So we can see here that verbal test loads highly on factor 2 and math and logic load highly on factor 1. However, the interpretation will usually be clearer after rotation of the factor pattern. So once again, just going over the factors here and what they mean, we can see that the first factor is most highly related to the math test and the logic test. But the verbal test loads also quite strongly, 0.512, which isn't that bad. So the factor seems to represent general intelligence. The second factor has a high loading on verbal ability, but negative loadings on math and logic. So it looks to be like a bipolar factor of verbal ability versus math and logic ability. However, there's another much clearer interpretation that will be obvious once we have rotated the factor pattern. Now your textbook on, I believe it's page 163, shows a vector plot of the data, and you can see if you rotate it about 24 degrees, factor 1 coincides very closely with math test, and factor 2 very closely with the verbal test. So we could call factor 1 a quantitative ability factor and factor 2 a verbal intelligence factor. Logic loads strongly on the quantitative factor, as can kind of be seen by here, but it's even better when you look at a vector plot, but also slightly related to the verbal factor, as we'll see in the rotated vector plot on page 163. And I'm also going to demonstrate this using another table. So what I'm going to do is, this is, you see I've labeled unrotated, and I'm going to do a magic trick to make it rotated. So I'm first going to highlight some rows here. Let's start on, let's do the 12th. Let's go down to 20. And unfill these and watch this magic trick. Ready? 1, 2, 3, bam! Okay, I cheated, but here is the rotated factor analysis summary table. And we'll explain rotation more fully later on, but just give you an idea, after we do a rotation, the factors, the variables load thusly. So we see that the verbal test doesn't load as much on factor 1, but math and logic load even more. Well, math does, logic not as much, but it's still very high. And on factor 2, after our rotation, verbal test loads even higher on factor 2, and math and logic pretty much stay the same at a very small correlation. Thus, we can say that factor 1 might be a quantitative ability and factor 2 a verbal ability. And we can do the same process that we did before of just getting the communalities. It's pretty simple. Total communalities. So the eigenvalues can be the sum of these divided by 3. Can move that across. And then this is going to be the eigenvalue divided by 3, and I know I did that wrong. I'll fix it. But let me just do this across. I didn't mean to do the divided by 3 yet. There we go. We can even extend this because going to move this down, and you'll notice the uniqueness doesn't change. Why do you think that is? Well, that's always going to be true because the rotation does not change the amount of variance in each variable accounted for in the space of, in this case, 2 factors. Rotation basically just simplifies the interpretation. It's not going to change any of the amount of variance in each variable accounted for. So there you go. I know this video took forever. We're at 40 so minutes now. So we just went through steps 1 through 15 in pretty much calculating from scratch, demonstrating from scratch a complete factor analysis using just really simple data. And we ended up having a factor analysis table, and then we rotate it in order to better interpret what the factor loadings and things mean. So I hope you enjoyed this. I hope this was beneficial. If you want to know how to do this on software programs, statistical software, just go to the supplementary videos on this. Hope you have a great day. Sorry for taking up all your time. I love you.